So the last few things here, we know capacitors are used to store energy. So it would be pretty useful to know how to calculate how much energy they store. And so that's, there's a handy formula here that uses every possible variable related to a capacitor that you could possibly want. And so here are the 3 variations on calculating the energy stored in a capacitor. It's energy, so of course the units are joules, and this shows you how you can get joules, farads times volts squared, or coulombs squared per farads. So if you want to use your capacitor to save up energy, like I was saying, in a perfect world, we could have these giant capacitors outside of every neighborhood and store up as much energy as we needed to weather, you know, like World War III. So that would be awesome if you could do that. If you wanted that energy, you could just discharge the capacitor and get the energy back out again. But any capacitor that sits long enough, its energy is going to slowly decay away. So that's why this proposition doesn't really work.
Realistically, how long does a capacitor really hold a charge? I mean, just a ballpark idea.
I have no idea. I think it would have to relate to the type of capacitor, how well it's made, what it's made out of. Does anybody have insight, like, you know, beyond my knowledge? I don't know, but maybe you guys have taken a class where they mentioned what causes the charges to leak off a capacitor?
Well, no, there's an ambient, because it's not a perfect isolation.
Mm-hmm.
So there's slowly charge dissipating as it goes, you know, back through to itself or to anything else in the circuit. So if it's, but if you were to just charge it up and unplug it, I think it's for a couple of weeks. I think.
Okay.
Depending on, you know, obviously if it's a really tiny one, then it's not going to last as long as one with a much larger capacity, you know. So you got to take that into account.
Yeah, I mean, I have heard the idea proposed of having these neighborhood power stations where you would just have capacitor banks, and that would get you through like brownouts or blackouts or, you know, little power events that can be resolved within 24 hours. But I don't think it could be like a long-term solution. Yeah.
The ones that capacitors for cars. I mean, I think it's, you know, to store charges like a hybrid car.
I don't know anything about that actually.
Yeah. So
Yeah.
that's something that they've talked about, I think.
And if you charge up like a capacitor, like in a lab setting or something like that, for it to discharge enough, like to where it's safe for you to, you know, touch both ends or whatever without like electrocuting yourself again. I think it's just a couple of hours.
Oh, really?
Yeah. So it's not, but that's like the small.
The little ones. Yeah. Yeah. I mean, yeah. I think it would depend on, you know, the size, how much energy it's holding, and then how well it's insulated from, like how isolated you could get it from everything else in the circuit, you know.
Just, unplug it after it's like fully charged.
Mm-hmm. Yeah, so I mean, those are things that are going to become increasingly more of a concern for everybody, like as well. I mean, I think it already is a concern. We just haven't found a good solution yet. But you know, there was that issue a couple years ago where there was some eco-terrorists that took out some power stations in California, and it caused brownouts for like really big sections of the state. And it was like suddenly really obvious how vulnerable our power system, our grid in this country is, and that we don't have these little substations that can fill the need for, you know, I mean, if the power goes out, the power's out. So it's something that we need to address, and that, you know, whatever.
Similar with the big storm. I lived in Florida and Orlando, and I got hit by 3 hurricanes like every 6 weeks, one fall.
Yeah.
Like,
yeah, I mean, I think that
hurricanes hit Orlando, and it was pretty miserable. Like everyone was out of power for like at least a week. Yeah, yeah. I mean, those natural disasters are the case too. I mean, I lived in a neighborhood where the power lines to the neighborhood, a tree fell on them. And so we had no heat in the middle of winter for 3 days. That was the snowstorm of like '06, where
the whole city was shut down and all the freeways were like iced over, and they were just like, just don't leave your house. And we're like, okay. So we just bundled up and like walked to Joe's. You guys remember Joe's? I miss Joe's. You remember G.I. Joe's that had everything?
Oh, yeah.
Yeah.
I didn't know what you meant by Joe.
Well, they switched their name right like a year before they went under. Yeah, so it was Joe's. Joe's had everything. So we would just go to Joe's and walk around and be like, it's warm. Anyway, so yeah, this is a useful equation you can use a lot. If they asked you energy density, that doesn't come up too much. Energy density would be charge per unit volume? I'm trying to think if that's volume or area. Nice that I'm blanking on that right now. Book, tell me. Energy density, energy per unit volume. Okay, thank you. Thank you, book. So energy density has a lowercase u, which is kind of hard when you're writing to make that look different than the capital U. So that's energy per unit volume. So you'd have units of joules per cubic meter. So our equation is 1/2 E naught times the electric field squared. Okay, so add that to your list. All right, so we're just going to glance at these examples really quick. I don't know that their calculations are too complicated. Just want to make sure we understand the situation. So example 24/7, we connect capacitor C1, which is 8 microfarads, to a power supply, charge it to a potential difference of 120 volts, then disconnect the power supply. The switch is open. Okay, so basically you're going to take a charged capacitor and it's charged up to 120 volt potential difference. You're then going to take that capacitor and use it to charge up a second capacitor C2. So that's the picture we're shown. We're not showing the battery part. We're just shown the charged capacitor C1 and then it connects to C2, which is uncharged. So the first thing we're looking at is what is the charge on capacitor C1. So before, oh, this is starting to dry out. I hope Shelly can read blue. So before we connect C1 to anything else, we just have this capacitor which is disconnected from everything else. A potential difference of 120 volts. And a capacitance of, what was it? 8 microfarads. So what are we going to do to solve for the charge on C1? I'll call it Q1. What's the equation that'll get us there?
Q equals C delta V.
All right. So 8 microfarads, remind me what the times 10 to the what is? Minus 6, there we go. All right, and so we can solve that, and that is 960 microcoulombs. So 9.6 times 10 to the minus 4 coulombs. So that's part A. Part B is what is the energy stored in this capacitor? Okay, so we have the charge on it. Now we want to find the energy stored in this capacitor. So we've got 3 choices of an equation. Which one do you want to use?
We're looking for what? Potential energy?
Yeah.
First one, you split over 2.
Sure. So this capital V, that's the potential difference,
Okay.
not volume. Yeah, I know that's confusing because I just said energy density was per unit volume. Yeah, this is the good question, Savan. The V in the potential energy equation is the voltage, the potential difference. Okay, so we can put in our number here. For C, or for charge, square it, divide it by 2 times 8 to the negative 6 farads. And survey says 0.058 joules. Okay, and the book tells us they want to call this U initial. So that's a good idea because we're going to have a U final when this capacitor connects to capacitor 2. So that was parts A and B. Part C. Okay, so now we connect C1 to C2. So C2 has no charge to start with. It's 4 microfarads. We connect it to C1 in parallel. So the picture doesn't make this readily obvious. If you draw the circuit like this, C1 and C2, it's not obvious that they're in parallel. So to help me remember that, I like to draw an extra set of lines that come off C1. And that would be where the battery was connected to C1. You could throw a little switch in here since we closed that switch. So these are in parallel. Okay, so that's important to note. Okay. So C2 is 4 microfarads. After the charge no longer flows, what is the potential difference across each capacitor, and what is the charge on each capacitor? So we actually have everything for parallel capacitors over there. So what did we say about the potential difference across capacitors in parallel? Are they added or are they equal?
Oh, yeah, they're equal.
They're equal, yeah. So nothing changes. This capacitor has a potential difference of 120 volts. When it connects to this capacitor now has a potential difference of 120 volts. So it's the same. And then, make sure the book agrees with me. The book does not agree with me. Ignore everything I just said. Okay. Okay, so we have to take into account that C1 is going to lose charges to C2. Yeah. So its potential is going to drop. Whatever it drops to will be the same. C1 and C2 will be the same, but it's not the same as V initial. All right, so V initial does not equal V final. Sorry. All right, so we need to find V final. We need to know how many, so this had this many charges sitting on it, and as soon as it connects to C2, C2 is going to steal as many charges as it can.
It's only half as much, so it's just, should it be half?
Well, I mean, qualitatively, yes. Let's make sure we can do it with an equation. Okay, so I called the charge we solved for in part A, Q1. We're going to change that to Q initial. So that's the total number of charges that gets split up between C1 and C2. So we know that Q initial has to be equal to the sum of Q1 plus Q2. And then to figure out what that breakdown is, we can plug in our definition of Q. This is really similar to what we have over there, which is C1 delta V final plus C2 delta V final. So I make these deltas. So all we do know is that the final voltage across both capacitors will be the same. And so when I put it into this equation, then I don't need to have subscripts on the delta V. So I'll pull out delta V final. And then I can solve for it. So that's the only thing in this equation that I don't know. All right, so delta V final is Q initial over C1 plus C2. Okay, so Q initial we said was 9.6 times 10 to the minus 4 coulombs. And then C1 plus C2, we have 8 and 4 is 12 times 10 to the minus 6. Okay. And book tells us that the answer should be 80 volts. Okay, so that's good we checked. So the voltage is 80 volts across both, and we want to find the charge on each capacitor. So now we can go back to the equation that we had here and figure it out. Okay, so from that, we know that Q1 was equal to C1 delta V final, and Q2 is equal to C2 delta V final. Well, let's see. We don't need to calculate it, right? Q2 is going to be whatever Q1 is divided by 2. Since this is 8 microfarads and this is 4 microfarads, so this would be Q1 over 2. Okay, so Q1, if we calculate that out, 8 times 80, 160. No, that's not right. 640. Okay, so that's Q1 is 640 times 10 to the minus 6 coulombs, and that makes Q2 what?
$320.
Thank you. I'm just making sure you guys are still with me. All right. Last part, part D. What is the final energy of the system?
At the very end?
Yeah.
Like, after
After they've,
eternity?
nope.
No.
After they've transferred their charges, we're assuming these are perfect physics capacitors that never lose their charge. Nice try.
That's an easy answer.
That would be easy at infinity. After the charges have distributed, but no charges have leaked off. So when we calculated U initial, we used Q squared over 2C. So they want us to give the final energy of the system. Okay, so that's the combination of C1 plus C2. So the method we used before was Q squared over 2C. So the Q squared part we could keep the same because we know that the charge initial is the same as the total charges added up for both of them final. But C, that's tricky because we've got two capacitors. So we could find the equivalent capacitance and put it in there. Well, that would work. So we could say Q final squared over 2CEQ. That would work. Or we could save ourselves the trouble and we could use this equation where we know the voltage is the same for both capacitors. So we could do 1/2 the total charge times the voltage that's the same for both of them. So that should give us the same answer. So we'll try that. 1/2, and then Q final and Q initial was the same. So 9.6 times 10 to the minus 4th coulombs. And then we calculated V final was 80 volts. Let's see if the book decided to do it that way. Yep. Okay. 0.038 volts, or joules. So we have less potential energy than when we started. Is that surprising? No? Why not? Where did that energy go?
You're using energy when you're making all this, when it's going into something else.
Okay, so the energy goes to moving those charges. That makes sense. It's better than if we had a greater energy. That wouldn't make any sense, right? If U final is bigger than U initial, then you know you did something wrong. All right, I'm going to skip example 24.9. It's the spherical capacitor problem. You can see the book solution, but you know, as we said, it's not a very practical application. So I think just for the sake of time, I'm going to skip 24.9, unless anybody wants to see it. Okay, I think so. I know, Dave. Okay, my battery's still working. All right. The last topic is dielectrics. So as I said, having an air-filled capacitor is really not ideal. It's less efficient than having a dielectric, and you have the problems that the closer the plates are together, you've got the risk of them bridging. So having a dielectric between your plates is what you would have in normal conditions. So all the calculations we've done up to this point are for theoretical air-filled capacitors. And so the next slide is just saying this is what happens when you actually have a dielectric. So dielectric is something that's non-conducting. So what are some insulators we figured out from lab 1? Plastic. Glass, that was another one. Wood, yeah. Porcelain, sure. Yeah, ceramics. Yeah, they use ceramic a lot for these. Silk? Yeah, I think all of the fabrics are actually insulators. Typically, they're going to use some kind of, styrofoam, some kind of plastics are what they use for dielectrics. And then they can tweak the chemistry to make them better. So they allow a low gap. This increases the allowable potential difference, increases the capacitance. And we describe the properties of the dielectric with a constant capital K. And all of that is just what is the capacitance without the dielectric? Or sorry, what is the capacitance with the dielectric over what is the capacitance without the dielectric? So it's basically an improvement ratio. So how much did that capacitance improve by having the dielectric there? So you can see from the equation that it shouldn't have any units. Okay. And there's all of our equations once you've tacked a K on. So you can rearrange this K equation to solve for the new capacitance and then plug in our definition of what capacitance was based on the area and distance between the plates. So that's how you could find the new capacitance. I'm just going to call it C new to differentiate it. So K E naught A over D, and they like to combine these two terms into a new term called E. So it doesn't have a name, it's just K times E naught.
And that's our same E naught?
This E naught is the 8.85 times 10 to the negative 12th, yeah. And then this E would be dependent on whatever your K value is.
But K is not a constant, so why is it combined into this other?
Well, this would be a constant for a specific dielectric. So if you looked up in a table, like a certain material would have a K value. And so these are constants based on materials. And so then every material would have a new E naught, or E value. Let's see, did I say what table the K values are in? I don't know if they...
It's based on a
okay.
K value.
24.1. So it says a vacuum has a K value of 1. Obviously, if you had a perfect capacitor, there'd be a vacuum there, so there'd be no difference. Air has a K value of 0.00059, so it's basically 1. And then on the opposite end of the extreme, so K values are always 1 or bigger. That's kind of important to note. K is greater than or equal to 1. Okay, so the biggest K value in this table is strontium titanate with a value of 310. Water is second biggest at 80.4. That's interesting. Okay, so basically this just shows you that we can just tack a K on the front. Anytime you have an E naught in your equation, you can put a K out front and it becomes an equation for a capacitor with a dielectric. Anytime you have a C in your equation, if you put the K in front of the C, that would be your dielectric calculation. So, and then the electric field equation is down here. Let's see, this diagram shows us what happens to the capacitor if you add a dielectric to it. So if this capacitor had charge per unit area of sigma and minus sigma on each plate, if you add a dielectric in there, dielectrics can build up charge, but they're static charges. So it'll start building up extra charges on the outer walls of the dielectric. So you end up with an increase in charge inside this dielectric material itself. Let's see. The induced charges in the dielectric reduce the electric field between the plates. So then there's less lines in here. Okay, so let's try our hand at some dielectric problems.
Does that mean that the capacitor is less efficient with the dielectric in there? Having less lines? Less field lines?
No, the amount of energy stored is more related to the how much potential you can have. So you can have a bigger potential if you've got a dielectric between the plates. So bigger potential difference is directly related to bigger Oh, I see what you're saying though, because the potential difference equation has E in the numerator.
I'm just curious, just the field lines are being less, you think that would mean that was less?
It wouldn't have anything to do with its efficiency. Efficiency would be how well it can store its charge over long term, but how much charge it can hold.
Since it reduces the electric fields, and I think that's what the errors are signifying.
So this equation says the capacitance increases, right? Because the K value has to be greater than 1. So you have a greater capacitance. And then our capacitance equation, our charge equation is capacitance times potential difference. So if your potential difference was the same, you would have more charges on the capacitor. So it could hold more charge for the same potential difference. Yeah, I mean, the dielectrics do improve things. Yeah, they are improving. Yeah. Okay, so example 2410, we're going to skip step F. All right, and I think this is just one of those like solve everything you possibly could about a capacitor with and without the dielectric. So I'm going to let you guys go on this one working in groups, and I'll walk around and answer your questions. And I think this is a good summary for the day, so we're going to stop here. And then if you have more questions, 2411 I think is the same. 2411 is the same circuit as, or same capacitor as 2410. They just ask you 2 extra questions. So if you did all of 2410 and all of 2411, you'd like answer everything you could possibly answer about a capacitor. So I'll let you guys work on those in groups and see how far you can get. And you know, there's a lot of questions, so if you're stumped on one question, try and go to the next one, just so you're making progress through as many of these questions as you can. Again, you don't have to do step F. And then we'll come back together in 5 minutes or so and see if you guys got stumped on anything.